and momentum. But for now, we just want to take a mass balance approach to this and think through it a little bit. So remember, we won't have class Thursday this week, so Thursday, March 25th. We will be back on schedule next week. We'll have class Tuesday, March 30th, and then again April 1st, of course. And the next homework number 9, that is posted. It's been posted since last week, and that'll be due next Thursday, April 1st. Okay, so what do we mean by this? Let's talk through this a little bit. We want to look at mass conservation for moving, non-deforming control volumes. Okay, so when the control volume is moving and does not deform, so it's not a balloon, it doesn't deform. So we could think about a rotating object like a sprinkler. We must, let me get my pen going here. We must consider what we call the relative velocity. Which we're going to call W. Okay, so capital W, in general, it will also potentially be a vector. So I'm going to add a vector notation to that. And we can define the absolute velocity as the sum of the velocity of the control volume and the relative fluid velocity. Okay, so what this looks like then is V will be our absolute velocity as seen by an observer. An observer in a fixed coordinate system. And then just to give myself a little room, I'm going to do this, is equal to W, which is our relative velocity we just identified or defined at the top of this. So that's going to be equal to W, which is our relative fluid velocity and this is the velocity sort of as seen, I'm going to say, by an observer moving with the control volume. Okay, so in other words, it would be like if you were Ant-Man and you got really small and you sat on top of, let's say, the spinning arm of the sprinkler. What would the W is basically, if you were moving at that velocity, the velocity of the spinning sprinkler head, W is what you would see the water coming out at, or whatever fluid is coming out. Okay, so V, our absolute velocity, is equal to W, the relative velocity, plus your book uses this value U, okay? And U is, in this case, the velocity of the control volume as, oh, goodness sakes, CV, as seen by, or from, I guess would be better, as seen from from a fixed coordinate system. Oh. Okay, so ultimately you can probably expect that W and U might be going in opposite directions. So V is ultimately the sum of these two vectors that might be going in opposite directions. All right, and we'll illustrate that here in a moment. Okay, so our continuity equation for a moving and non-deforming, so a rigid control volume, is the same as for a stationary control volume, except the absolute velocity is replaced with a relative velocity. So in other words, we don't just look at V now, we are looking at W, coming out of the nozzle. So I'm just going to say this, of the fluid. Okay, which might help this a little bit. All right, so I've interjected this image on the right-hand side. Don't worry too much about it because we'll see it a couple of times over. What I wanted to point out simply is that with respect to using the Reynolds transport theorem or other continuity equations, the key is that we have to focus on the flow out, right? W is telling us what the velocity is of the water coming out of the nozzle, but V is incorporating that W and the velocity of this control volume as it moves, okay? These heads in this case, or these arms of the sprinkler. So we can't get thrown off by V. We can't necessarily get thrown off by U. We have to focus on W with respect to part of this. But from a mass balance perspective, this is fairly straightforward. What we're going to do next week is talk about linear momentum, where V and U will play a bigger role. Okay. At the moment, we're just going to focus on kind of the W component of this, given that we may have V involved and U involved. Okay. So what this looks like then is the continuity equation turns into this. Oops, I forgot out front. Del T of the integral over the control. Well, that's curious. Of the control volume. Don't know how that happened, but anyway, sorry, that's del T of rho dV. Remember, this is basically how much mass is stored in our control volume. So how that changes with time, plus then the exchanges, recall, across the control surface, the mass flow across the control surfaces, which define the boundary of our control volume. So now we have, instead of V, we're going to have rho times W dot N hat dA. Okay, so this is defining rho times W is the mass flow of the mass, in this case, coming into the control volume and leaving the control volume, right? So we can think about it in the picture on the right, and we'll look at this in a couple of examples. There's some mass coming up from the bottom stem into the middle of the vertical part of this sprinkler, and then we have water going out the two arms of the sprinkler. All right. So here's what this example looks like. Let's just take a look at this. So we've got section 1 coming up through here. So this is a Q1, and this is also a Q1, right? And then section 2, the water coming out, we have some Q2 and some Q2 at some velocity W2 occurring there as well. So Q1 is actually equal to Q2, right? we are taking all of Q1 and splitting it into two arms. We expect evenly, and so half of it goes out one nozzle of the sprinkler head, and one goes out the other nozzle on the other part of the sprinkler head. So we are given a rotating sprinkler where water enters its base at 1,000 milliliters per second. So that is a flow rate. If the exit area of each nozzle is 30 square millimeters, determine the average speed of water leaving the nozzle relative to the nozzle if the sprinkler head rotates at 600 RPM. So we're essentially being asked for W. Okay, what is this relative velocity? All right, so first of all, let's just state that we know that the first part of our continuity equation that I wrote on the previous slide, the change in time of the storage of water, so the integral over all of the volume of the density in our system, that's going to be equal to zero, right? We don't have any information about a change in storage inside of this fixed control volume. So what we need to do then is just focus on the exchanges, right? The second term will have our exchanges. So recall, well, let's just do this on the next slide so I don't run out of room here. Okay, so over here real quick, we said 2Q2, all right? And there are two Q2s here. So here's a Q2 and here's a Q2 as well. Right, so both of those add up to Q1. All right, so first of all, we can expect that the mass flow rate at point 1 is equal to rho times Q1, right? That's something we've defined before. So our mass flow rate in looks like that, and the mass flow rate out, of course, is m dot 2 is equal to rho Q2, and as I mentioned before, Q1 is equal to 2 Q2, okay? So we can relate these mass fluxes, but let's do this in sort of a proper way. So we said that the second term of our mass balance is the most important here, our conservation equation. So the integral over the control surface of rho times W dot n hat dA comes down to being equal to 2 times the mass flow rate at points number 2, right? There are two of them. So the two of those outflows, so I'm just going to call those outs, minus the one mass flow rate in, so we can call this the inflow rate, mass flow rate, is equal to 0, right? That they have to balance each other. What comes in must go out. So if we now replace with these terms up here, then we would have 2 times rho A2 W2 is equal to rho times Q1. Okay, so on the left-hand side, I took one extra step. I substituted in the rho times Q2, but I changed that Q2 to be area times velocity. Okay, so here's the area. A2 is going to be the area of the nozzle, and W2 is the velocity of the water coming out of the nozzle. Okay, we haven't considered anything about the spinning of this sprinkler head just yet. Okay, now of course we can simplify this to say the rows cancel on each side, and so we can solve for W2 as being equal to 1,000 milliliters per second times 0.001 cubic meters per liter. So that's just a conversion factor, okay, that I've included here to get us from milliliters to liter. And then times, well, I have another conversion factor, but that's for the denominator here, which is 1,000 milliliters per liter. Sorry, I realize now I'm sort of confusing this. We went from milliliters to liter with what I just did in the denominator. We went from liters to cubic meter in the numerator unit conversion there. And then we've got times 2, right, in the denominator. And then we also have the area, which we were given to be 30 millimeters squared. And then we just need to change in the numerator. I'm just going to call this 10 to the 6th millimeters squared per square meter. Okay. Ugh, it's supposed to be a 2. Okay. So when we do all this math, we basically end up with W2 is equal to 16.7 meters per second. Okay, so that's the velocity of the water coming out of the end of the nozzles, okay, both of them. So W2 is the same in both locations. We haven't figured out a W1, but it didn't really matter much. We were given a flow rate, so we didn't have to work on that. We weren't given a diameter for the inflow, so we can't say much about that velocity coming in. All right, so number 1, I want you to note a couple of things. One, W is this relative velocity is independent of the rotation of what we call omega, which is the rotational velocity of the sprinkler itself. So those two things don't matter to each other, all right, in this case. 2, the absolute velocity this U that we have here, this recall that we said, well, let me go step back. The absolute velocity V2 we said was equal to W2 minus U, right? That is because we expect these going in opposite directions. So the water is coming out one direction, but the sprinkler head is going in the opposite direction. So W and U are acting in opposite directions. We would expect U in this case to be equal to omega times R. So omega is this angular velocity, and R is the radius of this. And we didn't need any of that in this case, okay? So that part where we were given the information about the spinning of the angular velocity, we could end up ignoring in this case. We will use that in the future. So I think we're coming back to this problem next week when we'll look at linear momentum instead and start to think about forces. So for the purposes of just looking at mass balance, all we needed was W here, the velocity of the water coming out of the nozzle. Okay, which makes sense. However, it is coming out of a control volume that is moving. Okay, so you can think of it this way, that Q out is not affected by the velocity of the control volume, therefore V out is not affected either, and it is relative to the velocity of the control volume, okay? And so we essentially need to use W in, this should be a capital W, please don't confuse that with omega. We need to use W in our mass balance equation instead of V. Right, because V is taking into account the speed of the rotation of our control volume in this case. Okay, so last 2 slides here coming up. So just to explain, for the sprinkler example, if we stop the sprinkler from rotating, the velocity of the fluid exiting the control volume would be the same as when it was moving. Right? So let's think about that for a second. If we have a constant flow rate of 1,000 milliliters per second coming into this control volume, then what's important here is that all of that volume has to go somewhere. So whatever comes in has to go out, right? So if we stop the spinning of the sprinkler, we're going to still have 500 milliliters per second coming out each of the two nozzles at the end, right? Because we have 1,000 coming in, and we assume that it's evenly split to the two exits. When the sprinkler is rotating, the absolute velocity which is V of the system, has a relative volume or pardon me, relative velocity, not a relative volume. Relative velocity component, which is sort of fluid that is exiting the control volume, and this control volume velocity component. It should be a C. And this is U. Okay? Which are each acting in opposite directions from one another. So essentially, then on the next slide, I'm just going to note what that equation looks like. And the reason that I wrote it the way that I did on the previous, through the example. So V is equal to W minus U, which is to say that for this particular system, W and U are acting in opposite directions, right? So I'm going to leave this in vector form because we want to indicate the directions here. But even if they weren't in vector form, essentially we know that U is acting this way. It's supposed to be a U, and W is acting that way. Therefore, V is ultimately the sum of those two acting in opposite directions. Okay, so in this case, we see W is greater than U, and therefore V has some magnitude to it. It's positive in that same direction as W, even though this thing is spinning in the direction of U. Okay. All right, I hope that makes some sense. We're going to go over this with respect to, I'm not sure why this says streamline coordinates, but in any event, this is along the streamline. So we're working with V, U, and W working more or less in the streamline, even though this thing is rotating. So with that, I'll go ahead and wrap up. I hope you guys have a good rest of your week, and I'll look forward to seeing you next week. Take care.
I'm not going to the beginning. I'm with Springfield, Joe. With your
Springfield's gonna be my turn.
Huh?
That's what you used to.
Yeah, man, you would be the lucky one.
Well, you guys are gonna go first,
One!
I always get one. I never get 10.
Wait, did you get that last time or that was just fraud?
That's the only one. I only get one. Every time I get one.
One is nice, it's a lot.
Every time.
Oh, you're first. It doesn't matter, you're first.
That's amazing.
That's amazing. You don't want to be first?